Hello, everyone. My name is Chen. I'm a member of the infrastructure team here at Baidu USA. And this talk, the main topic will about to enabling the multimedia data support in large scale on Spark and related applications at Baidu. And so for the motivations, so basically what kind of the multimedia data we are talking about and why we even need to process multimedia data on Spark or for the business at Baidu. So basically the multimedia data we are talking about have two different types. The first type is those like your cell phone's image, videos, or voice or music uploaded by the user. So those are the first kind of the multimedia data we want to process. The second type of the data is actually machine-generated binary logs compared with rather than the text logs generated by the human users. So for example, you have a temperature sensor, you have a 3D laser sensor, or you have your camera mounted, and you want to somehow capture and analysis those data, those machine logs captured by those sensors. So those are the second application I'm going to talk about. So basically, there are many interesting applications at Baidu involving multimedia data processing at a very large scale and serving all kinds of the product and customer requirements and handling various type of the input multimedia data or the binary data input format in general. So in this talk, I will just cover two interesting applications as examples. The first one I'm going to talk about is the Baidu's image search application. In this application, we do an image feature extraction and transformation for CTR prediction application. And this is more like a traditional multimedia type of the input. The input is the image, basically pictures uploaded by the owner of, for example, some online retailer shop. And the second application I'm going to talk about is the high-definition map generation and simulation for self-driving cars. So basically, the first application actually was developed in the last quarter of the last year, and currently the application is in a very late stage of going into production. And the second application for the self-driving cars currently is a very active project here at Baidu USA, and so it's an ongoing project, it's an ongoing effort. So basically in this talk, I will just mention those two applications one by one. I will focus on the first application because that's when everything started, and the second application is an ongoing effort. I will just spend the last couple of slides to quickly go over. So let's start from the first application example. It's about the Baidu's image search. So in this application, we have billions of the image in need of feature extraction and transformation for multimedia understanding tasks. And a common workflow for this kind of application, if I'm going to give an example, is initially the owner of maybe some online retailer shop, they upload certain pictures into our online service. And those pictures could be the product they are trying to sell or the service they are trying to sell. And there could be some other pictures like a barcode or maybe a photograph of their building or their website. And the first part, we actually do an image recognition and classification on large scale of those pictures daily in order to distinguish which are the really product photos we need. And after the first pass, given those product photos, we actually do a second pass is to rank those product photos to select a number of the candidates we want to demonstrate, want to show on our website. And in the very last pass of this pipeline, what we do is we actually including those multimedia features, in this case, image feature, extract from those pictures to actually combine those features into our CTR prediction model to better predict the behavior of the user. So that's the first application, the pipeline. And what's the major challenge we are facing in this kind of application? The first one is we need to have certain core functions of the core user logic to do the feature extraction job. And given such kind of the core functions for feature extraction, because your input is not just like one single or a couple of image, you want to handle a very large scale like billions or at least maybe several millions of the image. And so the key is really how you can efficiently to do a large-scale distributed execution of those feature extraction logic with your input data support on multimedia data. And last but not the least, we want to develop our new functionality that, so that this distributed execution can benefit any existing feature extraction executable, even those executable were never really designed in the first place for the Spark to run. And we want the whole design to be flexible and easy to use for platform users. And so in the next several slides, I will talk about how we tackle those challenges one by one. The first one is about the feature extraction called user logic. For this one, I will give an example of a very simple one, actually, what we use in our testing. So in this example, the feature extraction program was written in C++, and it had a dependency on Baidu's internal CDN library. It's an in-house library. And in its turn, this CDN library also has a dependency on the open source OpenCV library. And what this call function did is basically to compute the, maybe I won't go to the details here, but the key takeaway of this slide is about typically for this kind of the high-level multimedia data understanding or data analysis job, the program, for one reason or another, they typically write in C++, and they typically have layers on layers of the dependency on other external library. So it's not really easy, or I can say it's not even very practical to rewrite all those user logic into native Spark application so that you can directly access the data inside the Spark RDD. So the most painless way for the user to actually use this kind of functionality is to go to the Hadoop streaming for one option, or in the Spark terminology, is to go to the Spark pipe way. Spark pipe. In that way, the user don't need to rewrite their logic, just rely on the Spark pipe to go in and out of the platform. And so back to our end-to-end requirement, the input is a large amount of the original multimedia files you want to understand or you want to process. And the scale could be billions or several millions of the image. And the output you want is a high-level feature descriptions just extract from those huge amount of the image. And you maybe just want to do some processing on those multimedia files. One simple example is if your input is a JPEG image, maybe you just want to do a rotation of those JPEG image on those millions or billions of the image. And so the output could be processed multimedia files. Or maybe you want to both of them. And the other requirement from the customer could be the database of the original multimedia file they want to process could be constantly changing and adding. So the job needed to be run frequently or daily. And there is the need for the faster iteration because sometimes the user want to tune in the parameter. They want to change their method for extract or understand the multimedia files. They don't want to wait many hours or days to get the feedback. And so this is the end-to-end requirement. What we can do to this requirement, one thing we can do is obviously we have the user logic, the executable binary, and all those dependency library, you load it into one machine, and you try to process all those data. So a very naive example is you just assume that you have a very fast algorithm to extract the features. In that way, you only need 200 milliseconds for each image. And in this single machine, you have 16 tasks running perfectly in parallel. There is no computation for resource. There is no failure or whatever. And in this case, if you want to process 100 million of image, it will take more than 14 days to finish the feature extraction task alone. So what we can do, obviously, we can distribute the whole workload into a cluster like 500 machines. And then the problem will become how you manage this cluster of 500 machines, how you split the input, how you collect the output, how you handle the failure and the retries. So what we do in our final solution is obviously we turn to Spark for help. So the original multimedia data is divided into partitions of the data or split of the data, and the workload is distributed into the executor node in a cluster. And there is actually one missing link for this diagram. So today, as far as I know, I believe you just cannot simply connect everything easily and make the whole flow from input to output work because currently the Spark don't have the support for multimedia or general binary data format input and output. Spark doesn't have such kind of like the I/O support. So what we do is we introduce the binary piped RDD in Spark to make this a reality. And in the next couple of slides, I will go into a little bit of technical details of how this thing is built on each executor node. So basically, it's a data flow of the binary signal on each executor node. Originally, you have a partition of your original multimedia files. And on each executor node, I draw two boxes. The left box is the platform space, which means the original Spark executor logic plus our newly introduced binary piped RDD logic. On the right side is the user space. So this all the user logic happen, how the user do the feature extraction or processing of the multimedia data. And so basically, as the very first step inside the platform space, we do a simple encoding and serialization. So this is basically the first encoding step is to convert all the data types from the user. Maybe the file name is a string, the length of the multimedia content is an integer. So everything is converted into a byte, raw byte format. And after that, we do a serialization. It's almost like you put all those multiple multimedia file data structure into a single unified array of the bytes. And after that, the single unified array of the byte is handed over from the platform space into the user space. And what is happening in the user space is kind of like very much similar and symmetric to the platform space. So inside the user space, after receiving this one single unified stream of the input, it do a deserialization to break down into different stream of the multimedia files and do a decoding to recover the content. And after that, each multimedia file is fed into the user logic to do the feature extraction or maybe to do the multimedia understanding or processing one by one. And after that is purely symmetrical. You do an encoding and a serialization to result a single unified stream of in the form of the byte, and then you hand over from the user space back into the platform space. And at the platform space, initially, you have a local collection of the output paths in the format of a byte RDD, basically. And here is actually a branching point, really depending on what kind of application you are trying to support. For example, your application is trying to, among each partition of the image, you try to select the very best image. You just need your result is probably the index of that image plus your ranking score or something like that. And so this local collection of the output bytes could be something really small. And then you can just do a collection, Spark collection from your RDD into your master collection of the bytes. And then you can interpret your data whatever way you want. But in some application scenario, this may not be the case. For example, you are just process the multimedia data file. And so your local collection of output bytes could be a very large in terms of size. It could be a one-to-one correspondence with your input multimedia file, just processed. So in this way, we actually provide another branch. We can, inside the platform, to do a deserialization and decoding to recover each processed multimedia file. And then it's the responsibility of the Spark worker to upload those separate processed multimedia file into a distributed file system. So just two different branches to support different application scenarios. And here, I also want to mention some implementation highlights of this whole system. So basically, we utilize the Spark's capability for in-memory computation. And all those computation, all those data carry in and carry out you see in this slides is actually happen inside the memory. And we make a very early design decision to actually build everything on top of our streaming mechanism. That means for each box you see is basically a stream stream writer followed by a stream reader, and then another stream writer followed by another stream reader. So what I really mean by this is actually the whole pipeline, inside the whole pipeline, there is never a big chunk of the multimedia data buffered anywhere inside the platform or inside the user space. This could be very important because you have a huge amount of multimedia data. You cannot afford to have such kind of the buffer mechanism. And one benefit we get from this kind of the design is the memory requirement for the whole pipeline could be very much constant and fixed. And just like any design decision, it is basically a trade-off. So we understand that for such kind of the design, a streaming-based implementation, it will be very appropriate for application like a feature extraction or multimedia data processing. In those applications, you basically pass through all the data from the beginning to the end, just once, and you process the data sequentially one by one. But if your application you are trying to support by this pipeline is like a model training kind of like a application, then this design is not going to work very well because typically in model training, you try to buffer all your data in the memory so that you can make several passes through the data through many iterations. But it's just like I mentioned, it's a design decision we make based on our business requirement. And there are several other implementation highlights I want to mention. First one is, as you can see from the previous diagram, all the data serialization and encoding happen inside the Spark RDO space. Thus, everything is linear scalable, which I will give an experimental result in the following slides. And we actually support a very flexible output formats because the original format is in the raw bytes. So you can easily support feature vectors, ranking scores, process the binaries, or anything, almost anything. And it is very easy to plug in customized encoding and serialization function directly into the platform. This I will show an example in the next slides. So basically, if the user are not very happy with your default serialization or encoding logic, they have the freedom to plug in their function into the platform, which will be executed distributedly. And last is we can support passing Spark's internal information into some legacy application or user logic, which requires things like partition ID or task attempt ID. And so, yeah. So in this slide, what I'm showing here is actually one example. It's an early prototype of how this so-called binary piped RDD looks like in the declaration part. So you can see we actually provide flexibility to the user by providing 3 optional plugin functions. The first optional plugin function will allow the user to put in a customized context header at the beginning of the binary stream. So these are ways of the communication between the platform and the user space. So as you can imagine, this can be one possible ways of transferring those Spark internal information like a task ID or partition ID into the user space. And the second and the third function is, like I mentioned, is for the optional plugin function for encoding and serialization and decoding and deserialization, so that the user can override the default logic of the platform. And for the performance result, we were running on a very fairly small Spark cluster, and we are processing 11,000 of the image inputs with archive function. And I think we still have time. Maybe I will mention. So one of the major challenges when we try to push this functionality into online production is really about how you can serve a large amount of the multimedia file into the Spark. So if you have, like in this example, if you only have 11K of the image, that's not a problem. But if you have a million or hundreds of millions of the input image, you cannot really just put them on any standard distributed file system that will quickly overrun the master node because you have so much metadata in your memory. So one solution we have is we actually build a archive function using some codec internally, multimedia codec internally in Baidu to actually group a subset of those multimedia files into an archive. And in this way, we actually somehow bypass this kind of problem. In our implementation, we also support a generic codec like the zip-0, for example, this kind of the codec. And the other option we are currently actually still working on is we want to have a dedicated profile serving mechanism directly into the Spark Executor. So this is an ongoing effort. So last year we are trying with tagging, and this year is called allocation. I heard tagging is become allocation, and we are still exploring this direction to do a dedicated profile serving of the multimedia data. And so back to the performance result, what we do in this experiments, we actually change the number of the CPU cores in each experiment, and we record the end-to-end runtime of the whole job. As you can see, when we increase the number of the CPU cores, we have the total end-to-end runtime decrease linearly, so showing that roughly we can process about 5.6 image per core per second, and the whole performance is linear scalable. And going into production, we predict if for 100 millions of the image, and if we have 10,000 of cores, that will take only half an hour. And in the reality, when finally this function go into the production, we found that among those whole database, we only have 3 million of image incremental every day, so we only use 500 cores cluster, and within 20 minutes, we can finish all the feature extraction job. So that's all for the first application. The second application is a current ongoing effort at Baidu USA. It's about self-driving cars. So how this had anything to do with the multimedia support, how this had anything to do with the Spark. So in the self-driving cars, basically we have 3 different types of the maps. The first one is for navigation. This is a regular, you can see, for example, from the Google map. The second one is the HD map used for planning and controls. It has all the traffic lines, the traffic intersections, the signals, everything labeled. And the last but not the least is a very important one is the intensity map built by 3D laser scanners. So this is the map is used for perception task. For example, for the high precision localization of the self-driving vehicles. As you can see, those are the things we want. Those are the output we want. But they are obviously not in any kind of like the plain text format. They are in original binary format. And some of them, you can say they are in the multimedia format. And what are the input to this whole generic HD map generation pipeline? The raw data is actually gathered by a 3D laser scanner mounted on your self-driving cars or your data collection cars. And those raw data from the sensor, obviously they are in original binary format as well. And after some pre-processing, we produce the point clouds from those raw data, and we do some alignment to produce aligned point clouds. And after that, the aligned point clouds are projected into a 2D space to produce the 2D intensity map, which is exactly I was showing on the right side. And after that is some labeling of the map to produce the final planning and control map for the final movement planning and control of the vehicle. So what we really did is the data challenge in a self-driving car project. So for the back-end data center job, there are 2 typical jobs. One is to generate the map. The other is to do the simulation. They're actually starting from the same point of gathering those data. So let's just assume we only have one single 3D LiDAR scanner on this car. But even for this one single sensor, the data rate is almost 40 megabytes per second. And if we count all those 2D and 3D sensors in a self-driving car, the amount of the data we need to record and process is around the terabytes of the data per hour per car. And this actually causes a lot of trouble if you don't have a very good and reliable and efficient distributed computing platform. So for the HD map generation, basically in the previous slide, I already mentioned the pipeline. So the goal is really to one of the key component is how you align all those point cloud. And what we are trying to do this year is we actually put all those point cloud alignment algorithm into Spark worker, and using the binary pipe, the RDD mechanism I mentioned in the previous slide to parallel efficiently execute on Spark cluster. And the other thing is the simulation. For simulation, basically you have those large amount of the data coming in, and large amount of the data coming in, and what you do is actually a replay of those data to see what will happen if you change some parameter of the car, or if you change some critical component of the car. And for this thing, it's a similar story, because when you do a simulation, you want to see your result within a very timely manner. You want to replay a whole 24 hours of data, but you don't want to wait for 24 hours to see the result. You just maybe tuning some small parameter. And so the parallel execution of those simulation tasks is really the key of simulation component in self-driving car project. So that's all for my talk. So basically, this talk, if you look at it in the broad topic, they talk about the general data intelligence and analysis on Spark. But if you really zoom in, so into the technical aspect, it really only talk about how we enable the binary input format and combined with a pipe-based user program binary or library execution. And to the best of our knowledge, when we started this project last year, this is a missing functionality in Spark, even in Hadoop. And we believe this is a very crucial function going forward to enable large scale of the multimedia support. And so we introduced the binary piped RDD as a platform abstraction for input data in their original binary form. And the data can seamlessly streaming to and from existing executable. And we make it really easy to use for the user, so that even those executable are never designed to be parallel executed on Spark, so they can still plug in. And in the experimental result, we demonstrate a linear scalability with input data. So that's all.
Thank you, Kwan. It was a good follow-up after Andrew Ng's talk this morning. Questions? No questions. There you go.
So my question is, how do you partition your binary input?
How we
do you partition your binary input?
Yeah. So basically, the binary input, like I said, it could be a large number of the multimedia files. So basically, the Spark will do the partition work. So the partition work is not a component of the binary piped RDD. So, but the partition could be a problem because it's not a problem for small JPEG file, but your input file is if they are very large. And for example, you only have 10 of such file, but you have 100 machine to distribute the output. Then it becomes a problem how you actually partition the single multimedia file into multiple split of the data. So this could be a problem. But for our case, because we are processing JPEG file, each JPEG is maybe 300K or 500K. So that's not a problem.
Thank you for the good presentation. Didn't understand actually the concept of RDD versus binary RDD. What is a binary RDD?
Yeah, actually I remember, let me think about it. This actually is very much technical. I believe before our work, the binary RDD is already existing. At least when I really did this work last quarter, I already see there is a binary RDD already existing there. But that one is actually just to linking the input. So basically, you can already read the binary data into Spark. So that's what we call the binary RDD. But there is no way you can encoding and serialize those data and hand over to the user space and collect the output back. So that's the missing functionality I was talking about. But I don't really know the recent development, but as far as I know, last year there is already the binary RDD existing, and it can read in binary data and store them into this RDD.
Anyone else? Okay, well, thanks a lot, Kwan.
Okay.
Give a big hand.
Thank you for coming.